Next section, we're going to talk about simplifying radical expressions. And so in order to simplify them, we need to know what they are. Radical expression is any expression that contains a radical, such as a square root. So if you have a radical, you can simplify it, if it's not in already simplest form. So first you need to decide if it's already in simplest form. So the radicand is in simplest form when there are no perfect square factors other than 1, which means that if you factor it, for example, 3 is 3 times 1. The only perfect square in there is 1, so you can't simplify it any further. But if you had a perfect square, 9 is 3 times 3, so you have a perfect square factor, so you can take it out. If you had, for example, 12 is 4 times 3. 4 is a perfect square, so it's not simplified. You also can't contain any fractions under the radical, and you can't have any radicals in the denominator. Okay, and in order to simplify, we're going to use the product property of square roots, which states that for any non-negative real numbers, a and b, the square root of ab is equal to the square root of a times the square root of b. So what that means, basically, is if I have the square root of ab, that's equal to the square root of a times the square root of b. So, for example, if I have the square root of 36. Well, no, 36 is a bad example. The square root of 12, what we just used, is equal to the square root of 4 times the square root of 3. And the square root of 4 is 2. I can't simplify the square root of 3. So that would be 2 times the square root of 3. And there's a couple different ways to approach this. We can identify perfect squares. Or we can factor completely. All right, so if we're talking about identifying perfect squares, 80. I know for a fact that it has a 4 in there, and so does 20. So I have two perfect square factors, 4 and 4. So 80 is the square root of 4 times the square root of 4 times, the square root of 4 times 4 times 5, which is the square root of 4 times the square root of 4 times the square root of 5. So that's 2 times 2 times the square root of 5. So 4 times the square root of 5. So that's one way to do it. Another way to do it is to factor completely. I'll take 54 and it's even, so it'll divide by 2. And 2 goes into 54 27 times. And 27 is 3 times 9, and 9 is 3 times 3. And when we do this, we look for matching factors. Okay, let me take a step back. 54 became 2 times 27, so the 54 is gone now. It's 2 times 27. And the 27 became 3 times 9, and the 9 became 3 times 3. So we don't look at these numbers anymore. We only look at the very ends of the tree. And if you match, so 3 times 3, you can take the pair out. I can take the square root of it. 3 times 3 is a perfect square, so I can square root it and bring out the 3. Basically, if you match, you can go out. If you don't match, you have to stay inside. So this 2 stays inside, and this 3 stays inside. So this becomes 3 times the square root of 6. 180 is 2 times 90. 90 is 2 times 45. 45 is 5 times 9. And 9 is 3 times 3. I have two 2's. and 2 3s. Those can come out, and this 5 has to stay behind. So the square root of 180 is 6 times the square root of 5. If I were going to do this using perfect squares, I would have to recognize that 36 was a factor of 180. That's not always easiest to do. That's why I like the factor trees. Now, if I'm multiplying square roots, my first step is to multiply the radicands. And my second step is to simplify. So the square root of 2 times the square root of 14 is the square root of 28. 2 times 14 is 28. And 28 is 2 times 14. And 14 is 2 times 7. So I have 2 2's. So that can come out, and the 7 that has to stay behind. 5 times 10 is 50. The square root of 50 is, 50 is 2 times 25. Now, if you recognize that 25 is a perfect square, you can stop here and just take the square root of it. If not, you can continue to factor, and you'll get a pair of 5's and a 2 that has to stay behind. If you recognize 25 was a perfect square, you could just take the square root of it and still get the same 5. So there's 2 ways to go on that one. 6 times 8 is 48. 48 is 2 times 24. 24 is 2 times 12. 12 is 2 times 6. 6 is 2 times 3. I have 1, 2 pairs of 2's. So those can come out, and I have a square root of 3 that has to remain behind because it doesn't have a match. And so this becomes 4 times the square root of 3. So that's how we're going to multiply square roots. If we have variables, we're going to simplify the constant or the coefficient, the number part. And then on the variables, you divide the exponent by 2. If it's even, it'll go evenly, and so it'll all come out. If it's odd, it won't divide evenly, and 1 gets left behind. Okay, so first I'm going to deal with the 90. 90 is 2 times 45. 45 is 5 times 9, and 9 is 3 times 3. So I've dealt with the 90. 3 times 3 can come out, so the 3 comes out. The 2 and the 5 are going to remain behind, but I'm not going to take care of those just yet. I'm just going to leave them sitting here, knowing that I'll need to come back and leave those inside the radical. X to the third, 3 divided by 2 is 1, with a remainder of 1. So 1x comes out, and 1 gets left behind. So what happens now is I'm going to take these 2 and leave them inside. 1x comes out, 1 gets left behind. Y to the fourth, 4 divided by 2 is 2. So they all come out, and my new exponent is 2. Z to the fifth, 5 divided by 2 is 2, with a remainder of 1. So 2 come out, and 1 gets left behind. So let's try another one of those. 32 r squared k to the fourth t to the fifth. So I'm going to deal with the 32 first. 2 times 16. And I know that 16 is a perfect square, so I could take the square root of it. But if you don't recognize that, you can do 2 times 8, 2 times 4, and 2 times 2. I have 2 pairs of 2's, so 2 2's are going to come out, and 1 2 is going to get left behind. R squared goes evenly, and there's 1, so 1r. K to the 4th goes evenly, so there's 2 k's. And t to the 5th two with a remainder of 1. So 2 t's and 1 t is left behind. And then I'll need to simplify that. I didn't leave myself a lot of room there, sorry. So 4r k squared t squared times the square root of 2t. So one more. 56 is 2 times 28. 28 is 2 times 14. 14 is 2 times 7. 1 pair of 2's come out, and then the 2 and the 7 get left behind. There's 1x, so I can't really divide that by anything, so it stays inside. 10 divided by 2 is 5, so 5y's come out. And then 5 divided by 2 is 2 with a remainder of 1. So 2 z's come out and 1 stays behind. So what I end up with is 2y to the 5th z squared. 2 times 7 is 14 xz. This is completely simplified. The quotient property of square roots. Hold on one second. Okay, so the quotient property of square roots states that for any real numbers a and b, a has to be greater than or equal to 0, and b has to be greater than 0, can't be equal. Then the square root of a divided by b is equal to the square root of a divided by the square root of b. So essentially, what that means is if I have a fraction, then that's the square root of a divided by the square root of b. And that works out really well if I have perfect squares. I get the square root of 4 over the square root of 9, which is 2 over 3. Works out nicely. Sometimes I don't have a perfect square in the denominator, and that requires me to do what's called rationalizing the denominator. And to rationalize the denominator, I have to clear the square root out of the denominator. I'm not allowed to have square roots in the denominator of a fraction. It's not proper. So what I do is I multiply the numerator and the denominator by a factor, that should have an a in it, that eliminates the radical in the denominator. So we're going to make it a perfect square. So in order to do that, I'm going to take my square root of 35 over the square root of 15. I'm going to rewrite it like this. And I want to make the square root of 15 a perfect square. In order to do that, I'm going to multiply it by the square root of 15. Now I can do this because the square root of 15 over the square root of 15 is just 1, and I can multiply anything by 1. It doesn't change the value. And once I do this, what happens is these cancel each other because I'm squaring a square root. So I end up with 15. And then I'm going to do 35 times 15, which is 525. And then I need to see if 525 can be simplified. So I'm going to do kind of a sideways factor tree. 525 will divide by 5, and it's going to be 105. And 105 will divide by 5, and that's going to be 21. And 21 is 3 times 7. So I have a set of 5s that can come out. So this will equal 5 times the square root of 21 over 15. And 5 and 15 will reduce. So this is going to be the square root of 21 over 3. Now be very careful here that you don't make the mistake of saying, oh, well, 21 divides by 3, and so that'll be the square root of 7. But it doesn't work that way. I can't divide something in a radical by something that's not in a radical. So this is as far as I can go. That's my final answer. Let's try another. 6y square root of 12. So I'm going to multiply both of these by the square root of 12 over the square root of 12. And I'm going to get the square root of 6 times 12 is 72 over 12. And I'm going to see if I can factor that 72. And 36 is a perfect square. It's 6 times 6. So this is going to be 6 times the square root of 2y over 12. I can't bring out any y's because there's only one of them. And 6 and 12 will reduce. They both divide by 6. And so I end up with the square root of 2y over 2. And again, I cannot divide this 2 because it's under the radical. So I'm finished here. Now, I can skip the step where I write them separately if I want to, and go straight to that part. I'm going to try to see if I can simplify the square root of 450, which I'm very sure I can. It's 10 times 45, and 10 is 2 times 5, and 45 is 5 times 9, and 9 is 3 times 3. And I have a pair of 5s, and I have a pair of 3s. So those come out, and that 2 gets left behind. And I'm going to get 15 times the square root of 2 over 10. And 15 and 10 both divide by 5. And so I get 3 times the square root of 2 over 2. Again, I can't divide these 2's because one's under the radical and one's not. So that's my final, most simplified answer. Sometimes, oh, there should be an N there. Sometimes we can't just multiply by a single square root and get a cleared denominator. So for example, if I multiply this times the square root of 2, I get 5 times the square root of 2 plus 2. The square root of 2 didn't go away. So I have to use what's called a conjugate. And conjugates are sort of like binomial opposites. So what will happen is if I have a plus 2 and a minus 2, these are conjugates. So if I have a plus the square root of 2, or let's use numbers. So say 2 plus the square root of 3 and 2 minus the square root of 3. These are conjugates. And the reason we use conjugates is because if I multiply these together using FOIL, the square root is going to go away. So if I FOIL this out, I get 4 for the 2 times 2, and then I get plus 2 times the square root of 3 minus 2 times the square root of 3. First, outside and inside, and then last, I'll get minus 3 because the square roots will cancel each other out. Well, that makes these cancel out, and I end up with a single number, no more radicals. So if you have a binomial in the denominator, you have to use conjugates to rationalize the denominator and get rid of that square root. So whatever I have here, if this is a positive square root, I'm going to multiply by a negative square root. Okay. 3 will get distributed. So I end up with 15 minus 3 times the square root of 2. And then here I FOIL, but because I know that these are going to cancel out, I can kind of do a modified FOIL, or I can do the complete FOIL. So I can either do a complete FOIL, and do my first, my outside, my inside, and my last. And I will get 25 plus 5 times the square root of 2 minus 5 times the square root of 2 minus 2. And these will cancel. And I'll get 23. Or I can do modified. And here's what I mean by that. My inside and my outside end up canceling each other out. So I can just multiply first and last. And I get 25 minus 2. And this only works when you're using conjugates. Now you can't do this with a normal binomial. So only conjugates allow you to do this. Okay. So my denominator here is going to be 23. To reduce this any further, I need to look at these three numbers, the 15, the 3, and the 23. If they have a factor in common, I can reduce. If they do not, which these do not, I am done. So let's try this one. I'm going to take 3 over 2 plus the square root of 2, and I'm going to multiply it by 2 minus the square root of 2. That's my conjugate. So this was positive, this is negative. I distribute the 3 to give me 6 minus 3 times the square root of 2. And then I'm going to do first and last. And I get 4 minus 2, which is just 2. So 6 minus 3 times the square root of 2 over 2. 6 and 2 will reduce, but 3 and 2 won't, so I'm done. I stop right there. On this one, I'm going to multiply by plus the square root of 7 because it was minus the square root of 7. I'm going to distribute that 7. Actually, I'm going to rewrite this one just in case visually it's a little confusing. Okay, now I'll distribute the 7, and I get 21 plus 7 times the square root of 7. And then I'm going to do FOIL, or a modified FOIL, and I will get 3 minus 7. So I get 21 plus 7 times the square root of 7 over negative 4. Now this one I do need to simplify further because we don't like negatives in the denominator. So I need to change all the signs to get rid of that negative in the denominator and make it negative 21 minus 7 times the square root of 7 over 4. Okay, and again, 21, 7, and 4 don't have anything in common, so I can't reduce that. I didn't come up with an example for some reason where you would reduce, but let's just say I get something along the lines of 10 plus 5 times the square root of 2. Actually make it 15 over, I don't know, 20. These will all divide by 5. So this is the only time you can reduce. And you'll notice I didn't mess with the square root at all. And that's that.